At the end of this video, you should be able to compare the momentum of different moving objects, compare the momentum of the same object moving with different velocities, identify examples of change in the momentum of an object, and describe changes in momentum in terms of force and time. Chapter 6, Section 1, Momentum and Impulse. Linear momentum. When a soccer player heads a moving ball during a game, the ball's velocity changes rapidly. After the ball is struck, the ball's speed and the direction of the ball's motion change. The ball moves across the soccer field with a different speed than it had and in a different direction than it was traveling before the collision. The quantities and kinetic equations describing one-dimensional motion predict the motion of the ball before and after the ball is struck. The concept of force and Newton's laws can be used to calculate how the motion of the ball changes when the ball is struck. In this chapter, we will examine how the force and the duration of the collision between the ball and the soccer player affect the motion of the ball. Momentum is mass times velocity. To address such issues, we need a new concept: momentum. Momentum is a word we use every day in a variety of situations. In physics, this word has a specific meaning. The linear momentum of an object of mass m moving with a velocity v is defined as the product of the mass and the velocity. Momentum is represented by the symbol p. As its definition shows, momentum is a vector quantity, with its direction matching that of the velocity. Momentum has dimensions mass times length divided by time, so its SI units are kilogram meters per second. If you think about some examples of the way the word momentum is used in everyday speech, you will see that the physics definition conveys a similar meaning. Imagine coasting down the hill of a uniform slope on a bike without pedaling or using the brakes, as is shown on the screen here. Because of the force of gravity, you will accelerate. That is, your velocity will increase over time. This idea is often expressed by saying that you are picking up speed or gathering momentum. The faster you move, the more momentum you have and the more difficult it is to come to a stop. Imagine rolling a bowling ball down one lane at a bowling alley and rolling a playground ball, like a basketball, down another lane at the same speed. The more massive bowling ball exerts more force on the pins than the basketball exerts on the pins because the bowling ball has more momentum than the basketball. When we think of a massive object moving at a high velocity, we often say that the object has a large momentum. A less massive object with the same velocity has a smaller momentum. On the other hand, a small object with a very high velocity may have a larger momentum than a more massive object that is moving slowly. For example, small hailstones falling from very high clouds can have more momentum to hurt you or cause serious damage to cars and buildings. At this point, you should be able to understand sample problem A. A change in momentum takes force and time. Figure 1.2 on the screen here shows a player stopping a moving soccer ball. In a given time interval, he must exert more force to stop a fast ball than to stop a ball that is moving more slowly. Now imagine a toy truck and a real dump truck rolling across a smooth surface with the same velocity. It would take much more force to stop the massive dump truck than to stop the toy truck in the same time interval. You will probably also notice that a ball moving very fast stings your hands when you catch it, while a slow-moving ball causes no discomfort when you catch it. The fast ball stings because it exerts more force on your hand than the slow-moving ball does. From examples like these, we see that a change in momentum is closely related to force. In fact, when Newton first expressed his second law mathematically, he wrote it not as F is equal to ma, but in the form shown on the screen here. F is equal to delta P over delta T. We can rearrange this equation to find the change in momentum in terms of the net external force and the time interval required to make this change. This equation states that a net external force, F, applied to an object for a certain time interval, delta T, will cause a change in the object's momentum equal to the product of the force and the time interval. In simple terms, a small force acting for a long time can produce the same change in momentum as a large force acting for a short time. In this course, all forces exerted on an object are assumed to be constant unless otherwise stated. The expression F delta T is equal to P is called the impulse momentum theorem. The term on the left side of the equation, F delta T, is called the impulse of the force F for the time interval delta T. The equation F delta T is equal to delta P explains why proper technique is important in so many sports, from karate to billiards to softball and croquet. For example, when a batter hits a ball, the ball will experience a greater change in momentum if the batter keeps the bat in contact with the ball for a longer time. Extending the time interval over which a constant force is applied allows a smaller force to cause a greater change in momentum than would result if the force were applied for a very short time. You may have noticed this fact when pushing a full shopping cart or moving furniture. At this point, you should be able to understand sample problem B.
The momentum of an object is the product of its mass and its velocity. Momentum is measured in units of kilogram meters per second. A massive, slow-moving object may have the same momentum as a less massive, fast-moving object.
Stopping times and distances depend on the impulse momentum theorem. Highway safety engineers use the impulse momentum theorem to determine stopping distances, safe following distances for cars and trucks. For example, the truck hauling a load of bricks on the screen here has twice the mass of the other truck, which has no load. Therefore, if both are traveling at 48 kilometers per hour, the loaded truck has twice as much momentum as the unloaded truck. If we assume that the brakes on each truck exert about the same force, we find that the stopping time is 2 times longer for the loaded truck than for the unloaded truck. And the stopping distance for the loaded truck is 2 times greater than the stopping distance for the truck without a load. At this point, you should be able to understand sample problem C. Figure 1.4 shows a family playing a traditional game. Common sense tells us that it is much better for the girl to fall onto the outstretched blanket than onto the hard ground. In both cases, however, the change in momentum of the falling girl is exactly the same. The difference is the blanket, quote, gives way and extends the time of collision so that the change in the girl's momentum occurs over a longer time interval. A longer time interval requires a smaller force to achieve the same change in the girl's momentum. Therefore, the force exerted on the girl when she falls on the outstretched blanket is less than the force would be if she were to land on the ground.
When one object strikes another, the two are in contact for a measurable period of time, and forces can act between the objects during this time. The effect of these forces will cause the momentum of each object to change. The application of force over time to change momentum is known as impulse.
Force is reduced when the time interval of an impact is increased. The impulse momentum theorem is used to design safety equipment that reduces the force exerted on the human body during collisions. Examples of this are the nets and giant air mattresses firefighters use to catch people who might jump out of a tall burning building. The relationship is also used to design sports equipment and games.
A truck filled with heavy bricks is harder to stop than an empty one. This is true even if the trucks are traveling at the same speed. The heavier truck needs to start putting on the brakes when it is much further from the stop sign. Using Newton's second law, we see that the truck with the larger mass will have a smaller acceleration. We can also use the impulse-momentum theorem to understand the situation. Both trucks use the same braking force and have the same initial and final velocity. However, due to its larger mass, the momentum of the second truck is larger. If the applied force of the brakes is the same, we see that the truck with the larger momentum will require more time to change its momentum. The quantity force times time is called impulse, and it is equal to the change in momentum.
Consider a falling egg. When the egg hits a hard surface, like the plate shown on the screen here, in part A, the egg comes to rest in a very short time interval. The force the hard plate exerts on the egg, due to the collision, is large. When the egg hits a floor covered with a pillow, as is shown in part B, the egg undergoes the same change in momentum, but over a much longer time interval. In this case, the force required to accelerate the egg to rest is much smaller. By applying a small force to the egg over a longer time interval, the pillow causes the same change in the egg's momentum as the hard plate, which applies a large force over a short time interval. Because the force in the second situation is smaller, the egg can withstand it without breaking. At this point, you should be able to compare the momentum of different moving objects, compare the momentum of the same object moving with different velocities, identify examples of change in the momentum of an object, and describe changes in momentum in terms of force and time.